Recording in progress.
Hi students, in the last lecture I have discussed what is a capacitor, its definition, right? Let us see once. It is a device which stores electric potential energy and electric charge, right? Next, capacitance depends on the shape, size, separation between the plates and also the material that occupies the space between the plates. So we got epsilon naught A by D, right? Epsilon naught, because there we have taken between the plates air or vacuum. If you place something else, then in the place of epsilon naught, we have tried some other value. Okay, the meaning of material. Next is shape, like circular plates, square plates. It can be any shape. Depending on the shape, area changes. And coming to size. Suppose I'm taking circular plates. Shape is circular, but if R is more, area will be more, pi R square. So shape, size, and separation between them, epsilon naught A by D. If D value changes, capacitance changes. So capacitance depends on the shape, size, separation, and the material that occupies the space between the plates, right? And we can see how they appear, capacitors. This is one type of capacitors. You can see here 16 volt. This is a potential difference. And we can see here marking 100 microfarad. This is a capacitance. And this is now potential difference. Here you can see two leads. Okay, one is a plus and one is minus. And we can say this is a resistor, right? This is a resistor. Okay, these two are resistors. So I will get two leads. One is a plus and one is minus, right? And we can see here some more types. Fixed capacitors, mica capacitors, polyester capacitor, film capacitor, variable capacitor, paper capacitor, ceramic capacitor, electrolytic capacitor, and timber capacitor, having many types. We are having now different types. So how they appear, okay, like this. Let us focus now. In the last class, I have discussed up to definition and calculation of capacitance. Now, next one is a combination of capacitors. Let us see next one. So in this, we consider series and parallel combination. So focus on first series combination. Series combination. Let us take, this is notation symbol for capacitor having equal length, okay? Let us take two capacitors which are connected to a battery. So we should make a difference between battery and capacitor. Battery means one is longer and one is shorter. Coming to capacitor, both having same lengths. Suppose the capacitance is C1 and C2. And this is now potential difference V. So assume that initially the capacitors are uncharged, means no charges on the plates. Initially, the capacitors are uncharged. Now, once we connect like this, electrons will flow from the leftmost plate to the rightmost plate. That means the leftmost plate becomes plus Q and rightmost becomes minus Q. So this is losing electrons and this is gaining electrons. Since it is now minus Q, this will induce here plus Q. In the same way, Since it is now plus Q, this will induce here minus Q. See finally what happened? Plus Q, minus Q, plus Q, minus Q, right? That means we are charging the capacitors, right? Now we have to focus if we want to replace these two capacitors with a single capacitor so that for same battery, I'm taking an equivalent one. I want to replace both capacitors with a single capacitor so that for same battery, there must be same charge Q and minus Q. So for that, what should be the capacitance? Okay. So we want to replace both the capacitors with a single capacitor so that for same battery, there must be same charge. Let us see how we start. We can see here potential difference across the first one. So take it as V1. Across the second one, take it as V2. Then we can write V equal to V1 plus V2. So potential difference across first one V1, across second one V2. Then we can write V equal to V1 plus V2. Now in the place of V, I can write, see what we can write here in the place of V, Q by C, right? So we have relation Q equal to CV, V equal to Q by C. So I'm writing here Q upon C, that is equal to Q upon C1 plus Q upon C2. That means 1 by C equal to 1 by C1 plus 1 by C2. Okay. This is now equivalent capacitance for this combination. Okay. That means in series combination, condition 1, initially all are uncharged. This is a very important which we have to keep in mind. Initially all are all are uncharged. In that case, on each capacitor, charge will be same, Q, right? So we got 1 by C equal to 1 by C1 plus 1 by C. Let us take now parallel combination. Let us take it is now parallel combination. So taking two capacitors which are parallel to battery C1 and C2, and this is again we want to replace both the capacitors with a single capacitor so that, see here what happens. Suppose a Q charge flows through the battery. This Q charge is now dividing into, let us say Q1, and this is a Q2. Okay. So I can write here Q equal to Q1 plus Q2. Okay. So replace these two capacitors with a single capacitor so that for same battery there must be same charge. So for that, what should be the capacitance? Okay. So in the place of QC, what I can write? It is CV, right? This is now C1V plus C2V. That implies C equal to C1 plus C2, right? So when they are series combination, 1 by C equal to 1 by C1 plus 1 by C2. That means effective value is now less than the least value. It is effective value is now less than the least value. Coming to here, effective value is now greater than the greatest value. Suppose I'm taking here C1, 1 farad, C2, 2 farad, C3, 3 farad. If you take effective value, that will be less than the least value. Among these three, least value is 1. So effective value will be less than 1. If you take same thing here, effective value will be greater than the greatest value. Among these three, greatest value is 3. So here C value will be greater than the greatest value, means more than 3. Okay. Let's see what we have to discuss. Yeah, force between the plates of a capacitor. See how to calculate force between the plates of a capacitor. So we are taking now a capacitor charges Q and minus Q. So we have to calculate force by this plate on this plate. Let us do one thing. Because of this positive plate, field is sigma upon 2 epsilon naught. Field due to either positive charge or negative charge. Okay. Both value was same. Okay. Now what I can say is this minus q is in the field of positive charge. So field because of positive charge exert force on negative charge. Or we can see in the reverse also. Field due to negative charge exert force on positive charge. Therefore, that force will be equal to charge into field, right? Q into E. So Q only, E value sigma upon 2 epsilon naught. In the place of sigma, I can write Q by A. So Q by 2A epsilon naught. And that becomes Q square by 2A epsilon naught, right? So this is a force between the plates. Means a force by positive charge on negative plate or force by negative charge on positive plate. This is now force of attraction because one is minus and one is plus. It is just like a small problem, right? F equal to Q into E, E value because of one plate. So here there's a chance of making mistake because earlier we have taken sigma upon epsilon naught. But remember that that is a field due to both the charges. If I imagine here plus Q charge or unit positive charge, this is repelling and this negative attracting. So both fields are in the same direction. That's why we got field between the plates sigma upon epsilon naught. Sum of these two, okay? So you should be very careful while taking the field. So here we have taken field due to one plate, only one plate. But this is a field due to both the plates which are supporting. Both are in the same direction. That's why sigma upon epsilon naught, right? And see next one. Energy stored in the capacitor. Let us see how to calculate energy stored. Let us take initially capacity is uncharged. Condition is initially uncharged. Now connecting that to a battery. Suppose the potential difference is V connecting to a battery. It's a capacitance equal to C. So we have taken initially uncharged, right? Now once we're connecting a battery, electrons will flow from left plate to right plate. Or I can say from positive plate to negative plate. Let us take at one instant charge on the plates is Q, Q and minus Q. This is a charge at one instant. Initially charge was 0. At one instant charge is a Q. So this is minus Q. Now we can see at this instant, potential difference between them, that is equal to, see how to get now potential difference. We know Q equal to CV, right? Then V will be Q by C. That is now potential difference. Okay. Now take a small charge dq is flowing. How much? A small charge dq is flowing from here to here. Then see how much work is done to overcome now this repulsion. Okay. How much work is done? See here. Potential difference is Q by C into charge dq. Let us now calculate this. This is stored in the form of potential energy. See how much? Initially 0, final value. So take it as a Q. Okay. So from that, potential energy equal to 1 by C. Take outside Q dq, Q square by 2. It becomes now Q square by 2C. So this is the potential energy stored in the capacitor. This is the potential energy stored in the capacitor. Now this we can write it as, so here what is a Q means? Q equal to C into V, right? Using that result here, in terms of C and V, write here CV whole square by 2C. That is equal to half CV square in terms of capacitance and potential difference. Or this we can write in terms of Q and V. See how to take this one. This is Q in terms of Q and V. What we can write here? Q into Q by 2C. In the place of Q, I can write C into V, right? In the place of Q writing C into V, C gets cancelled. It is equal to half QV. Okay. So either in terms of Q and C, in terms of C and V, half CV square, or in terms of charge and potential difference. Okay. So this is the energy stored between the plates of the capacitor. Okay. Let us now calculate here one more thing, that is energy density. Energy per unit volume. See how much? Say here what we can write volume means. Energy is Q square by 2C by volume. This is volume. Volume is if area of the plates is A, separation is D. That is now volume, right? Then see what we get. Q square by 2 in the place of C. Epsilon naught A by D, right? See carefully. Into 1 by AD. See what we get. So here D gets cancelled. What else? Q square. A and A square. Q square. Q square. I can say Q by A whole square upon 2 epsilon naught, right? And remember, Q by A is nothing but sigma square, right? It is sigma square upon 2 epsilon naught. If you want to write this in terms of field, we know between the plates field equal to sigma upon epsilon naught. So I can write this in terms of sigma into sigma, okay? Sigma into sigma by 2 epsilon naught in the place of sigma by epsilon naught. Okay. Otherwise, what I can do is here, instead of taking like this, multiply and divide with epsilon naught. Multiply and divide half epsilon naught sigma by epsilon naught whole square. Okay. Now this is a half epsilon naught E square. So energy density is equal to half epsilon naught E square. Remember, this we have derived for parallel plate capacitor, but this is valid for any kind of configuration. This result we can use anywhere, not only for parallel plate capacitor. Okay. So energy density is equal to half epsilon naught E square. Otherwise, sigma square by 2 epsilon naught. Right? Let us focus now. See here we have taken while deriving energy. So we have taken that capacitor is initially uncharged. Right? See carefully. So we have taken the assumption that initially capacitor was uncharged. This is V and this is capacitance C. Charge equal to Q equal to C into V. Energy stored is equal to half CV square or Q square by 2C, or it is equal to half into Q into V, right? Now see carefully. When charge Q flows, okay, electrons flowing from positive plate to negative plate, or I can say Q charge is flowing like this, right? When Q charge flows from low potential to high potential inside the battery, so by battery work done is equal to Q into V, right? This is what we have learned, right? If Q charge flows from low potential to high potential inside the battery, work done is equal to Q into V. But remember how much energy is stored inside the capacitor? Half QV. So where is the remaining half? The remaining half is lost in the form of heat. That means when we are taking a capacitor which is initially uncharged, in that case, in the process of charging the capacitor, only half of the work done by the battery will be stored in the capacitor. Remaining half will be lost in the form of heat. So this is only when capacitor is initially uncharged. If it is initially charged, then that will be different. Okay. So which we are going to discuss that in the next lecture. So here what we have to keep in mind, initially capacitor is uncharged. When you are connecting that to a battery to charge a capacitor, work is done by the battery and only half of that work stores in the form of potential energy in the capacitor. Remaining half is lost in the form of heat. Okay.